All right, I'm going to work through a problem of beam reaction forces that we were talking about in class today, and I'll share my screen. And this reaction force is going to be caused due to a force coming down at an angle. So let me share my screen, and we'll work through it. So the beam is sitting there on points A and B, where point A is a pin joint and point B is a roller joint, and I have a 25-pound force coming down at a 60-degree angle, and that force is acting at 6 feet from point A, and the entire beam is 15 feet wide. So we're going to talk about reaction forces and how we break down the angled force into its x and y components. So it's going to be a combination of using components of forces and reaction forces. So let me draw my free body diagram down below. I'll start by drawing the same beam. And I don't always do my free body diagrams like this, but what I'm going to do today is I'm going to break down all of the forces. Instead of drawing this 25-pound force as an angle, I'm going to draw it in its x and y components down here to kind of show the idea of how we would break that down into its x and y components. So let's look at that. So I'm going to leave that 25-pound force alone up at the top, and I'm not going to redraw it. You can redraw it, but I'm going to choose to do it as x and y components this time instead. So I would have, at point A, I would have a reaction force, and I'll call that FAX. And I'm going to call, since I have my blue out, I have my reaction force of, and my component of that, and since it's kind of a component, it's not a true force, I'm going to draw it as a dashed line. And that force would be, and for breaking this down into x and y components, the x component of that force would deal with cosine of theta, because if I were to draw it like this, I have a force like this, and I have a force like this, and so my angle, my x component is the adjacent side of the triangle. So because it's the adjacent side of the triangle, and we're talking, so COTOA, the adjacent side of the triangle deals with cosine. And so cosine theta equals adjacent over hypotenuse. And so x is my adjacent side, so I'm going to say fx is equal to my hypotenuse, which is 25, times, I would move that over, times the cosine of 60. So this is going to be 25 cosine 60 is what that force would be. My y component then, because it would be the opposite side of this triangle that would be made, would be 25 times the sine of 60. So I'm going to have a y force acting down, and that's going to be 25 sine 60 for that value there. And I would have FBY, and I would have FAY. Okay, so that's what my free body diagram would turn into. So instead of redrawing the angled force, I simply broke it into its x and y components. And again, going back to the breaking down of component forces, you draw it as if it's a triangle. So if it's down and to the right, or down and to the left, I have a left force and I have a down force, and I can make those into a triangle, and then I use SOHCAHTOA to do that. And so my vertical force is the opposite side, so I would use sine of theta to figure out that component of the force, and my horizontal force is the adjacent side, so I'd use cosine of theta to figure out that component of the force. Okay, so now I can write I have my free body diagram, I can write down my equations of equilibrium. So I say sum of all the forces in the x direction have to be equal to 0. And so all of my x forces in this case, now before I just had a down force, so I didn't have any other x forces. So my FAX was equal to 0 because there were no other forces. But now I have a component of this force acting to the left. So my FAX is going to be offset, or it's going to have to offset whatever that force is. So I have FAX minus 25 times the cosine of 60. So let's do that really fast. So I'm going to do, on my calculator on my computer, I have to do it this way. 60 cosine is 1/2 times 25 is 12.5 pounds. So I'm going to write that down here. 12.5 pounds. And while we're at it, let's just figure out what cosine 60 or sine of 60 times 25. That's going to be 21 point, let's just say 7 pounds. 21.7 pounds. Okay. So now I'll do my, so I have one of my answers here. So I can write, if it's just these two, I can say, okay, if I were to cover that up, I'd have 0 is equal to FAX minus 12.5 pounds. So FAX, if I move that 12.5 over, FAX is equal to 12.5 pounds. So there's one of my answers right there. Okay. Some of my forces in the y direction are also equal to 0. And that's going to be FAY plus FBY minus 25 times the sine of 60 is 21.7 pounds. I can't solve anything more with that. I have two unknowns, but I only have the one equation here. So I have to have one more equation. So I'm going to use my moments equation that we talked about before. So some of my moments, and this time I'm going to write it like this. Some of my moments about point A. Point A is my hinge joint with the two forces. So I'm going to do my moments about the point that has those forces. And again, moments are caused by a perpendicular force to your moment arm times your distance. Now, positive moments act counterclockwise. So if I were to think of this as my pivot point, and this force is moving up, it would make that whole beam move like this. I'd be pivoting like this because that force is pushing up. So since that's counterclockwise, this FBY is going to be giving me my positive moment. So FBY times 15 minus the 25 is acting down, and so that would be going clockwise. The 25 sine 60, so it's 21.7 pounds times 6 feet. So if I were to work that out, I'd be adding 21.7, again, kind of cover this part up, so you have 0 is equal to FBY times 15 minus 21.7 times 6. So I could multiply that together, and I would add all of that over to this side. So if I do that, then I end up with, what's 21.7 times 6? Let's type that in. 130.2 is equal to FBY times 15. So now to get that by itself, divide by 15, divide by 15. Now over here, I can write FBY is equal to 130.2 divided by 15, 8.68 pounds. So there's another answer. Okay, so FBY is 8.68 because I rearranged and did all of that. So now I can plug in over here. So I can say 0 is equal to FAY plus 8.68 minus 21.7. So I would take all of this and move that over to the 0 side. And so then I could say FAY is equal to 21.7 minus 8.68, 13.02 pounds. So there I've solved now for FAX, FAY, and FBY, and I've also broken down my initial force into its X and Y components. So that's combining what we were working on with force vectors and component forces. And it's also showing how we would do a beam deflection problem. So if we have any questions, we can go over that in class, but hopefully that gets you started into using equations of equilibrium, beam reactions, not beam deflection, beam reactions, and component forces. So let's end it there in my screen share, and I will be back to answer any questions when we return to class. Good luck, everyone.